Okay, so I think earlier today when I was hearing from Tim's presentation about, the room is split into UEFI, 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 BIOS. Well, welcome to the ARM community. This is going to be even more fun. First of all, I think the majority of the ARM community don't know about BIOS to begin with. There's no such concept in that community. And also, a lot of the stuff that I'm going to be talking about are very new. And EDK2 is not necessarily the default implementation. In fact, it's probably the minority in that community as well. So when I talk about UEFI, ACPI, don't assume the underlying implementation is EDK2. So let's see how that goes. So to make the ARM ecosystem to accept and adopt more and more of these interfaces that we have done in this UEFI forum, what ARM has done so far is that we define this ARM Base Boot Requirement documentation that tries to leverage as much as possible the UEFI, ACPI, and SMBIOS concept into the ARM ecosystem. But I can't promise that everything is UEFI, ACPI, and SMBIOS, so that's why we actually have 3 different recipes for boot in the ARM ecosystem. And then after I talk about these 3 recipes, I also talk about our certification program that we have to try to bring the ecosystem together. But it's not one size fitting all, by the way. So for the firmware interfaces, we focus on the interface side. In this effort, we do not dictate what implementation is underneath the implementation. So we have this spec called Base Boot Requirements. Basically, it absorbs as much as possible ACPI, UEFI, Devicetree, SMBIOS into the requirements, and come up with these 3 recipes that I'm going to be talking about. They are targeting different usage models and different operating systems. And of course, we have been talking about secure boot, secure firmware update, TPM usages quite a bit in this forum. So we also have a document called Base Boot Security Requirements that, again, focuses on the interface side for these features. And these QR codes are where the specifications are published. It's all public. And this EBBR specification is related to this one of the 3 recipes for the embedded community wanting to support Linux. And basically, it is UEFI, actually reduce the UEFI profile for the embedded community. Most of them are going to be using UBoot. So the reason I try to stay away from the implementations is that implementation seems to be a high religion, right? If somebody is so used to UBoot, they're not going to adopt EDK2. If somebody is so used to EDK2, they're not going to use LinuxBoot. If somebody is so in favor of LinuxBoot, they're not going to change to UBoot. Right? You can see the pattern. So we try to stay away with the code bases, and they are all having benefits, advantages and disadvantages. I'm going to be touching on some of that, but we're not here to dictate what people want, wanting to do. We're just saying if you want to do this, you need to provide the baseline. So EBBR is for that embedded market. It has a reduced set of UEFI interfaces. And typically, people use UBoot to implement the EBBR with the minimum set of UEFI or UEFI interfaces. So when you see UEFI implemented on these embedded devices, it's not EDK2 below that. It could be. Some vendors do that, like actually NVIDIA, Jetson Orin is using EDK2, but that's not the typical case. Most of the people in that market is using UBoot. All right, so we also have a bunch of specifications related to how ARM presents some of the interfaces for power management or some of the CPU management. So we do have a set of specifications that are relevant where the base boot requirement document actually points to. So I'm just, for the sake of completeness, I put it in the slide. Anyone interested can search through that. In addition to that, ACPI, it started off from an effort on Intel x86 type of devices, but the architecture is actually ISA agnostic, so it can support ARM, right? And I think you can see other architectures being supported there as well. I think in the spec you now see RISC-V and Lansun or whatever architecture. So we did our effort in supporting ARM, and these are the specifications that are specific of ARM devices using ACPI technologies. We had to kind of plug some of the holes that are only related to the ARM SoCs. And so, we tried to push the common set of interfaces into the generic ACPI spec that the forum is owning. But for some of the features, if it's only related to ARM, then we at least start from owning our specs to begin with. If there are any reasons to move into the public, the UEFI forum domain, we could. But right now, it's these specs are kind of on the side. Let's see. So, given that background, I'm going to be touching on to how the ARM ecosystem are using these UEFI ACPI interfaces, for those of you who are interested. So we have 3 recipes. The first recipe is something that I think this room, people in this room can recognize very easily, right? This is not so much different from how x86 is using these interfaces. Basically, UEFI, boot time, runtime services, plus ACPI, plus SMBIOS, and then plus some of the ARM-specific interfaces like SMC and PSCI. We do have trusted firmware. Well, first of all, let me clear up for ARM, right? The 3 letters actually represented 3 different profiles as well, in addition to its legacy name. We're talking about A-class. A-class is where we support the rich OSs like Linux and Windows and VMware and other OSs. We also, in addition to that, have the R-class for real-time processing and also the M-class for MCUs. I'm not talking about the R and M classes here. So I'm only talking about A-class, where the rich OSs are expected. So this interface's definition or recipe is something that I think this room is very familiar of. And traditionally or typically, the underlying implementation is EDK2, but it's not necessarily the case, right? So typically it is the situation. But this EDK2 doesn't necessarily have the SCE or the PEI phases if you look into the implementations, because we on the ARM side has this element in the trusted firmware area. So the system, the SoC starts from the trusted firmware, and then as a package loaded on top of it, that could be the EDK2 pieces, but it doesn't have to start from PEI or SCC. And by the way, there is no SMM, so anything that people talk about SMM, security implications, there's no SMM in ARM. We do have this thing called trusted firmware, trust zone, but it's very different. It's not a big hammer approach where you issue the SMI into this big hammer thing that every core stops. No, we don't have that. Okay, so I talked about the eBBR. It's a second recipe we support. This is mostly in the embedded space. So we are trying to ask for the sake of having the easiness of porting Linux onto systems, we try to standardize on the UEFI interfaces. So as you can see in this recipe, we do have UEFI boot and runtime services, even though it could be reduced for the embedded space. But instead of using ACPI, this recipe today is only supporting Devicetree. So most of the embedded scenarios are involving Linux. So people who are in this community are so in favor of the easiness of the use of Devicetree, because it's just a flat text file of describing anything you want to describe about the system. So it's very easy to port these OSs using Devicetree to these devices. It certainly has a drawback because Devicetree is a description of the devices. It is not an abstraction. So what that means is that if you want your Linux distro to support your SoC, you actually have to upstream the silicon support into the mainstream and then expect to downport into the distros. It's not like you can do the forward compatible support for the OSs. So you can't just grab an image and expect all the silicon support is going to be there, right? Because Devicetree is descriptive, it's not abstract. The implementation of this could actually be EDK2. Like I mentioned, Jetson Orin actually does that. But typically it's using UBoot. In fact, people who are used to UBoot, they don't like EDK2. It's not like the coding style is something easier for them to understand. It's so difficult for someone who are used to the Linux implementations or the open source implementations. When they look at EDK2, they're like, this is so foreign to them. That's, it's just no way to get them to move over to EDK2. For people who jump the hoop and make this step function into EDK2, then they like it and they can basically promote it. But this step function is so huge that I don't see the easiness of people moving to that. And then you have hyperscalers. It used to be Google and Meta and ByteDance, and now it seems to be more ByteDance oriented. People want to use LinuxBoot. There is a benefit for LinuxBoot where especially for non-x86 architecture, where you don't actually have to rely on the availability of the UEFI drivers, the option ROMs. You can just take the Linux drivers and boot your systems. So there's a benefit. Also, another benefit is where the hyperscalers, when they staff people to manage the Linux OSs on their systems, it's very easy for the same people to understand the firmware code and use Linux in that scenario. So there's definitely some benefits for that. But of course, if that cloud needs to support multiple OSs, just because some OSs are existing on the UEFI interfaces, then you have to go to the SBBR route. So for today, the LBBR route, we have the first version of it, which is UEFI runtime services only. There's no UEFI boot services. And then ACPI and SMBIOS. And the implementation today uses the EDK2 firmware minimally to be able to support loading the LinuxBoot environment or the package. And that's all. They reduce the EDK2 components as minimum as possible. We have been working on this second version of LBBR recipe, and that's going to be presented next week, actually. between ARM and 9 elements. So I'm not going to be stealing the thunder, but this is just kind of a picture of what's coming. And basically the difference between this version versus the one before was that people don't like to have EDK2, period. So get rid of all the EDK2 code in the code base and use the Coreboot instead. So now we have trusted firmware loading Coreboot to supply the ACPI and SMBIOS information, but we need to have a way to report that to the OS. So we need to have this UEFI stub, which we actually leverage from the UBoot implementation, where we put UEFI on top of UBoot. Now we also have UEFI stub on top of Coreboot to support the very minimal structure to report ACPI and SMBIOS using the config, UEFI config table, and to also offer the minimum level of the UEFI runtime services. Remember, this one still doesn't have the UEFI boot services. The booting is still relying on the LinuxBoot to key-exec into the Linux operating system. The purpose of this version compared to the previous version is simply for the removal of EDK2, because people can't understand that coding style. All right, so I said that we don't care about the lower implementations. So it is actually possible to put another UEFI payload on top of Linux to support these other OSs, Windows, VMware, or other OSs. So there is actually work going on by Lenovo. I think Google actually did the first experiment, and then now Lenovo is working on that. So there's another session next week at OCP Summit that if some of you are there, you can listen to that. My thinking is that if that thing becomes more mature, then I really don't care, whether you use EDK2 or LinuxBoot, as long as you have UEFI, ACPI, and SMBIOS interfaces. To me, there's no difference between this version of LBBR versus SBBR. So we can collapse the two together. And I hope that will become a reality, because having three recipes just, it's like, oh, you have all three pieces for one. Okay, you get rid of UEFI to form another one. You get rid of ACPI to form another one. It's just, it's a bit of a mess in this, right? So we are hoping to reduce the fragmentations as much as possible, but still kind of taking care of the ecosystem reality. So the third piece I want to show about is how we actually are using the specifications to form a certification program to help the ecosystem to grow together and provide the customers the user experience that the OSs can just work. So, but to add to that, I talked about the firmware piece, but there needs to be a hardware standardization as well. So we do have additional specifications for hardware, minimum hardware requirements for getting the OSs supported. The BSA is really that piece. And then for servers, we are also trying to standardize additional requirements for the features, because the ARM spec is actually very flexible. You can do whatever you want, right? For a feature, you can have multiple ways of implementing, but that's not something the OS vendors can consume. So they would like us to kind of provide a direction, like, if you do this feature, this is how you do it. So given the hardware and firmware specs, we have basically created two flavors, but there are like three major things here. So basically the Devicetree approach is one way for the embedded market, and then the the ACPI approach is another way. And the ACPI approach can have two different sub-flavors depending on whether you build a server system or not. So that's kind of the major pieces. We also created, well, this is more detail, like which operating systems can you support with these different flavors of firmware, hardware combinations. Basically, IR is specifically Linux and maybe BSD as well, but for ES and SR, these are targeting all OSs, including Linux, but also Windows and VMware and other OSs. So we also have the LinuxBoot certification as well, but so far we only have certified one from Ampere. The market acceptance is not that high, so we're kind of putting it aside for the moment. People who are willing to certify, we can do that, but otherwise we just leave it on the side. We also created this virtual machine environment as well for the certification. So for hyperscalers supporting cloud instances, or for virtual machines on desktops like the Mac OS, the MacBook, we can support these kind of certifications as well. And also, I mentioned the secure boot and firmware update. We can add the additional support for that. I think in the future we're going to be requiring them because security is certainly very important. So just like Windows are now requiring secure boot and everything, we're going to be requiring that in the future as well. So we actually have a document that describes what are the how a device can certify for these type of flavors. We do have a test suite which builds on top of FWTS and UEFI SCT, and then we add additional test cases for the hardware and firmware compliances. And then we also test the OSs as well to make sure everything is in place. Virtual environment is very similar. We try to basically assume that you are trying to resemble a bare metal system, and we try to use the same test suite and OSs as well on top. We have a very large community supporting this effort from silicon vendors, firmware vendors, OEM, ODMs, cloud vendors, and so on and so forth. We also work with the open source community and some of the lab services also. Lots of devices that we have certified. Right now it's almost like around 40 devices for SR, which is the ACPI route, and also about 40 devices for IR, which is the Devicetree route. So they're kind of similar. And we support a lot of devices from different, using different silicon vendors, SoCs, and all that. So as you can see, for example, the HPE and the NVIDIA certifications that we have been working with, we are now certifying with the SIE, the security interface, the secure boot and update. So it's beginning to appear on the server side. It's also appearing on the embedded device side. So the nice thing about the IR is that now we have secure boot and secure firmware update support on these embedded devices using UEFI. The exact same, OS tools for the engagement, and also the exact same interfaces. Windows IoT is going to be interesting because it uses ACPI, right? The IR doesn't have the ACPI, so we're trying to find out a way to support ACPI on the embedded device as well, but it's going to take some effort. There has been some bespoke activities on that front, but it's more silicon vendor specific than kind of an industry effort. So this is one device that I mentioned for the LinuxBoot. And then we also had DPUs and some of the cloud edge, not cloud, the edge devices that are certified with ES. It doesn't have the server features, but it still supports ACPI. But the problem is many of these SoCs are not compliant to the hardware requirements. So we had to do a lot of interesting workarounds, to fake the PCI device, for example, to support these other OSs like Windows. The Raspberry Pi is a good example of that. But the NVIDIA Bluefield is actually compliant, so that's nice. And the ARM one is also compliant, but that board is very hard to come by. The Morello board is very nice, but it's very hard to come by. Right. So, like I mentioned, lots of embedded devices supporting Devicetree, using many different vendors' SoCs actually. All right. There are even some 32-bit ARM devices as well. And we also certify the virtual environment, so the AWS Cloud, Google Cloud, Microsoft Azure, Oracle Cloud, we certify them also. And then we did the FVP, which is our own simulation environment for our IP. We certify them, certify one of them at least as well. And also some of the VMs that are running on top of the Apple Silicon. That is it. Any questions?
Can you talk about the usage of FWTS and ACSOS to test the...
Yeah, okay, yeah, so what we did there was, after we defined the BSA, SBSA, and BBR spec, right, for the firmware and hardware requirements, we actually had this test tool called Architectural Compliance Suite, ACS. And so ACS basically leveraged the community, open source community work that we have from this group. So we leveraged the engine from UEFI ICT. We leveraged the Canonical's FWTS, the firmware test suite. We used both of them, and then but the SCT and FWTS focus on the firmware side of the story, right? But like I said, we do have hardware requirements. So we build on top of that test cases for the hardware compliance check. So now the ACS is kind of built on top of the same engine, but we added a lot more, compliance test cases, and it's open source. We have put it out there for everyone to use. In fact, we worked with OCP. We basically are asking, well, OCP already accepted this proposal that any ARM servers that are going after the OCP badge, OCP accepted badge, they need to go through the certification with us, right? And so we are contributing the test lab over there at OCP as well. We make the requirements as part of their requirements, and we're also going to be contributing the ACS to the OCP side as well.
Thank you.
When making a choice between UBoot and UEFI, does licensing not take a part of the decision making? That was sort of missing for me. I think UBoot GPL, right?
I believe so, yes.
Okay.
Yeah, I think the question was, is licensing consideration part of the choices on which code base you use? I would think so, right? But that's not the decision from ARM. It's the decision from typically the silicon vendors. And I would hope they must have considered that, UBoot being, I think UBoot is GPL, and EDK2 is BSD, right? And I think it also MIT or something, right? Is it? Anyways, it's not copyleft. And LinuxBoot is also copyleft to GPL. So, yeah, people should consider that at least, but I haven't seen that being a problem. It's more of, the group's mind share, right? If they already are heavily invested in UBoot, then there's typically no chance of moving them over to EDK2.
I don't think it's as much the silicon provider as the customer for the SIP, right, which is the ODM, right?
No.
If they're doing something in the embedded market, they're going to request UBoot.
No, so far I haven't seen that happen. I would hope so. I would hope the OEM, ODMs would have a say. But what my experience is not the case. I think it's basically the silicon vendors giving you this package, and they're like, you do it, right? So OEM, ODMs don't have a choice.
So you're saying the SIP basically decides, like, if this chip is selling to that market, you're going to get UBoot regardless of what you do.
Yeah. So typically, what happens today is like they're very focused on one particular market, and they typically customize the OSs, right? So they give you this BSP package, which includes the UBoot and and by the way, the UBoot may be many years old, which is another issue we're trying to solve, right? This UEFI on top of UBoot is a recent phenomenon. It is something that's available if you use the UBoot after, I think it was April 2021. But I'm seeing still silicon vendors using a snapshot of UBoot that was way back in 2017. Then they don't have this interface. And the problem is not that easy to say that, okay, move over to 2021. No, because they don't have this clear separation between the OS and the firmware, right? So they have developed all kinds of drivers based on the 2017 code base. And so if you're asking them to like, okay, can we move to this new code base? Well, all these drivers don't work.
The other problem is the UEFI implementation is it's not just a subset, it's a somewhat spotty subset. Like there has clear issues, but we didn't read the spec, we just implemented something. So.
Well, I think the EBBS spec is trying to be, governing that.
To a degree, but like, for example, like UBoot, if you use UEFI's UBoot implementation, you have a video screen, then we just blast the Unicode directly into the video memory without trying to convert it into some font. It's just garbage. So it doesn't give me much confidence about the rest of it.
Yeah, well, there's still some growing pain, I think.